these limits can be covered when you set up the Planck constant to the zero. So this is a very formal to show that the results are classical or not. You know, any quantity which you calculated in quantum mechanics, any calculations have a first classical approximations normally, and this is the classical value. And second is the quantum corrections. And if you set up this Dirac constant 0 or Planck constant 0, so do you know what is that? This is the average of the operator. Average of operator for a very long time, it looks like that, like a classical value. And then the other one are the quantum corrections. They are purely quantum mechanical. So any observer in the quantum mechanic observer have a classical part. Almost all of them has a part of the classical value plus some quantum correction like that. So this parameter you will see why this parameter will be important. Just you will see that it naturally comes as a parameter to make the equations in the better form and to make the analysis easier. I want to talk about the bosons. So what I want to know to calculate is that exactly I want to find the equation for the pressure and the number of the particles per volume and these things for the bosonic system. Do you know how this equation proposed this? This is actually the Du-Broglie wavelength. This equation is in one side is classical, in the other side is quantum mechanical. Quantum mechanics part is that the Du-Broglie say that find that you can define for each particle you can define the lambda for that. Even for the person who is walking, you know, if you are walking here as a normal person, you have a wavelength, but you know you never can detect that because it's very, very, very tiny number. So do you want to calculate that, for example, for the person with is 70 kilogram? So if what is your fastest velocity which you can have? A marathon normally finish in how long time, you know? I want to, in 1 second, in 1 second you can have, I don't know, 1 meter, is very fast, but anyway, 1 meter per second. I know this may be not realistic equation, but P will be mv, so around 17. So what will be the lambda? Lambda for that, H is 6 point something, 10 power minus 44, and we have what is that? This is just at the order of the 10, 70. So it will be minus 35 or minus 36. So it's very tiny number. So you never can detect that. The things which you can detect is a femtometer or something like that. 1 femtometer. Femto is 10 power minus 59. Or 10 power minus 12. These wavelengths you can detect in the optics labs. You never can get it. But it's very funny also to talk about the person like a quantum particle because quantum mechanics proposed for the tiny particle. Tiny means that the size of the atom, like that, angstrom. So this is not the angstrom. But anyway, I did this calculation just to have estimation. This equation, as I told you, is very fundamental. So in one side you have the quantum mechanics. So this is the, you know, it was the starting point of the quantum mechanics was the Broglie equations. So if you accept the Broglie, you can derive the Schrödinger wave equations from the Broglie principle. Did you ever see that? From this principle, you can derive the Schrödinger equations, and that was the starting point in some sense. So you have this here, but from other side, how to define the momentum for the particle in the gas, for example. You have a gas here in the box, so the particles are moving. How you can define the momentum for the particles? If you back to holidays, so in the holiday we define something, we call it the average of the square of the velocity, we call it VRMS, radical 3 kTm. K is the Boltzmann constant heat temperature, and m is the mass of these molecules. And the derivation is very elementary here. Do you know how to they derive? They just consider a particle, for example, moving in the z direction, so the momentum here will be m via z, and when the particle back will be minus m via z, so the total change in the momentum in the z direction is 2m via z. To find the momentum, or to find the pressure, or to find everything, you need the change in the momentum to calculate the change of the momentum. So pressure is, pressure is like the F average for the whole system over the area, and the F average is change of the momentum for total system over the time over A. And they consider the case that the particles are leaving this plate and reaching this one, so delta T is just going in the back, so 2L over Vz. You see how it's very easy, the derivations. So if you combine together, so you will find m Vz squared over La. But this is for z direction just, huh? So you needed to add this to the y direction and to x direction. You can find it that in the holiday is there, but I just want to write. So, and we make this assumption that the motion in the x, y, and the z direction are the same. So isotropy, the system isotropy. So there is no any preferred directions for the motion of the particle here. So what you can say is that in the average, Vx squared is equal to Vy squared plus Vz squared equal, and this is, we can call it V 1 over 3 of the average of the total velocity of the particle. So by this you can find the P, so P will be AL is V. 1 over 3, where is the 1, 2? So PV will be m v squared over 3. If the gas is idle gas, so you know that the idle gas PV is nRT or nKT. Of course, when you want to do for the all particle, you needed to multiply that to the n, because that was for one particle. So from here you can find the radical V average of the V square. Radical average of V square will be like that. Radical. So it gives you estimation about the average of the velocity of the particles, huh? It gives you that. So this is exactly what you needed, because to define the momentum for the particle, you need to have the estimation about the velocity of them. So if this comes from the kinetic theory, so it's a kinetic theory of gas. This is there is no quantum mechanics here, huh? This is just classical, yes? But this equation is quantum mechanics. For that reason, I told you this equation is different. In one side you have a quantum mechanics, in other side you have a kinetic theory. Kinetic theory is very old subject, 140 years. Boltzmann started that. And Dubray principle is 1920. It was a gap between 50 years to connect these two equations together. So from Dubray, for the other system will be, you have a quantum part here and you have a MV to record here. So it gives you the similar equation like what we call it thermal wavelengths. This is a thermal wavelength. So you remember the regime of the geometrical optics and the quantum optics. You know the difference of the geometrical optics and the quantum optics. When you can consider a system as a wave, and when you can consider a system as a particle. When? So you do the double slide experiment, for example, double slide Young's experiment. So you have a source here, so this is the size of the slide. So, and this is the screen. Because this I want to explain just why this related to the quantum mechanics, why this regime is important. You understand one thing is that how to define the lambda. Lambda comes from the unification of quantum mechanics and the kinetic theory. And n is the number of the particles, so this is not nothing special about it. Just I want to tell you that why this approximation tends to the, because there are some cases which this approximation is not valid. We are going to find the case which this approximation is valid, so to include the quantum mechanics. Quantum mechanics here is very important. Okay, tell me that this is not statistical physics. I want to examine your knowledge about the modern physics. So tell me that we have a source here. So this is a source. It will send some waves with the lambda. It can be any wave, any source, like any other. So tell me that in which approximation I will have here the continuous and I will have the just
right and left.
Yeah. I mean, when I can use the Newton optics and when I can need it to include the wave for my phenomenon.
When someone is observing, it would be particle. If no one is observing, it will act as a wave.
The fringes indicates that we are dealing with waves because we have destructive and constructive interference.
Yes, but you are talking about when you can consider this as a wave. But I mean, not always needed you consider the light as a wave. You know, light is particle also. So in Newtonian, you have a Newtonian objects, which you know that, for example, to consider, this kind of the experiment. Yes. There is a lens here, and the particle. So it was a very easy equations to measure the focal length. If you know the distance from the object to the mirror or not mirror, even the lens, you can find for me the distance of the pictures. Yeah. And this simple equation 1p over 1q is. But here, there is no any quantum mechanics here. There is no any things like the wave also here. It's just given. If you consider the light like a particle like that, you know, it's I don't know, like that. So okay, it's not very good shape. So this is Newtonian optics. So everything depends to the order of lambda and the d. You know that. So if the size of the system is tiny, and if the wavelength is also not so, you should look at that, because so a comparison between the lambda and the size of the experiment gives you the regime of the classical optics and the quantum optics. Quantum optics means that using the wave or actually wave optics or quantum optics. I call it this quantum optics. When you consider the waves, electromagnetic waves like the equation, like that. So just a comparison between the size of the system and the lambda gives you these approximations.
For a small slit, we will get away.
Yes, and it depends also to the value of the lambda. So for the short wave lambda, you can have the quantum, or you can have a discrete. If this size is very big, so you will have a continuous. So this is like that. So here in the particles in the gas systems, instead of doing such experiments to understand that what is the nature of the motions, so you needed to compare do you know what you need to compare? You need to compare, because the particles here are moving in the box. So, and you understood from this equation that, from the equation of lambda, h radical 2 pm cut t, you understood that there is a things which call it thermal wavelengths, and it's proportional to temperature. So if temperature goes down, so lambda will be increased. So if the temperature goes down, because this is the regime of quantum mechanics, quantum regime. Because in high temperature, I mean in temperature of the room, you don't need to consider these things. The particle here, the gas particle, are Maxwell particles, and they are distributed over the Gaussian Maxwell. When this calculation, I'm not sure that you get the idea of the last lecture and this lecture. You know, if you have a temperature, high temperature, you don't need it to be worried about that this is a fermion or boson or something. All the particles in temperature of the room looks like the same. You cannot label each particle. They are almost all the same. So this is the regime which you don't need it to consider quantum mechanics or psi or these things like that. Pauli exclusion principle or something. Or to be worried how many particles will be sitting with this. In the low temperature regime, why this physics is very important? Because we have a state of the matter which are very important for us in lower temperatures, like bosonic system, like the fermionic systems. For this reason, we need to know the physics of the low temperature. So there is a theory, low temperature physics. Low means very low. I mean, is actually near the Kelvin, yeah, minus 200 or minus something like that. Minus 200 at least. Not even minus, you can see that even something like 23 degree of Kelvin is very cold. I say minus but not minus Kelvin. So the temperature like 23 degree of Kelvin, so it's very cold. So This is very important for technology for us also to know that what's the physics. That reason that we need to use the quantum mechanics. For example, in astrophysics, before the calculation done by the Chandra-Sekhar, the Nobel laureate, he has a book about the mathematical theory of black holes. I want to tell you that before the Chandra-Sekhar do the calculation about white dwarf, you know what the white dwarf is? A kind of the solar object in stars like white dwarfs. Before the black holes, people had that some idea. Chandra-Sekhar was the person who think that because the temperature inside the stars should be negative, something like that, it will be cold, definitely will be cold. You needed to consider the quantum effect. He used the same calculations which you learn already in the book, like partition function and these things, and find the pressure for the inside of these stars, and find a limit for the mass to this. The astrophysical guys, they